In this video, I'm going to go through two examples showing you how to find the critical numbers for each function. And the primary goal in these two examples is really to review the trigonometry necessary to solve these algebraically to find the critical numbers. So first you need to remember that critical numbers are found by computing the derivative and then finding where it's equal to 0 and where the derivative is undefined. So in this case, the second term in this function, sine squared, that's actually considered a composite function. So it's important that you remember when you have a trig function raised to a power, that's really the same as writing the quantity sine of theta squared. So when we write 2 cosine theta plus sine squared theta, it's really 2 cosine theta plus sine theta, the quantity squared. And perhaps writing it this way will help you recognize that the second term is actually composite. So we're going to need to use the chain rule to compute the derivative. So f prime of theta, the derivative of 2 cosine theta will be negative 2 sine theta. And then the second portion here, since we have to use the chain rule, the derivative of sine theta squared will be 2 sine theta. And then we have to chain on with multiplication the derivative of sine theta, which will give us cosine theta. And if you've watched any of my other videos on finding maximums and minimums with critical numbers, I always like to factor my derivatives if possible. I find the algebra easier later on if we go ahead and factor now. So I'm going to factor out a 2 sine theta, and that'll leave me with negative 1 plus cosine theta. So this is the factored form of my derivative. Now we branch off, and I actually draw the arrows because I like that visual reminder so that I remember that I need to do two things here. I need to find where the derivative is equal to 0, as well as where the derivative is undefined. So because I have this derivative already in factored form, setting it equal to 0 should be relatively easy because all I have to do is set each of the individual factors equal to 0. So that'll give me 2 sine theta is equal to 0 and negative 1 plus cosine theta is equal to 0. So now I have two smaller trig equations that I need to solve. So dividing by 2 will give me sine theta is equal to 0. And then I need to think about the unit circle. Where is sine equal to 0? So if I'm on the unit circle, if I'm looking for the y value, I know the y value will equal 0 at 0 as well as over here at pi. And then if I continue looping around the unit circle, I'll get more values anywhere that I'm on the x-axis. That's where sine will equal 0. So those are going to be angles for theta of pi times k, where k is an integer. Now solving the second trig equation by adding 1 to both sides gives me cosine theta is equal to 1. So again, I'm back to the unit circle. I'm thinking about the x value this time. Where will the x value equal 1? And that's going to only occur here when theta is equal to 0, and then around the unit circle one full time again when theta is equal to 2 pi, and around another time, and that would be 4 pi, and so on. So this would be for theta values of, we could just say 2 pi k. So now we want to make sure that both of these sets of critical numbers are in the domain. So going back to the original function, because it was a function containing cosines and sines, the domain of the original function is all real numbers. There's no domain restrictions here. Therefore, these are going to all count as critical numbers. But it would be useful to recognize that really I don't have to include the 2 pi k values because as we listed those individual angles before, 0, 2 pi, 4 pi, and so on, all of these values are actually included when we write our set of angles as theta equals pi k. So it's somewhat repetitive to list them twice. Not wrong, just repetitive. So this means that we could say our final answer for this problem, which was asking just for the critical numbers. Our critical numbers are going to be pi times k, where k is an integer. Okay, let's do one more. Let's just find the critical numbers for this function. Now, on this function, we do have domain restrictions because this function contains a cotangent. So I think it's useful to actually rewrite cotangent in this case. Cotangent could be rewritten as 1 over tangent, or you could use the quotient identity and rewrite it as cosine over sine. I think it's easier to work with all cosines and sines, so that's the option that I'm going to choose. So cosine over sine plus 2 theta. So thinking about the domain, since we do have domain restrictions, we know that we cannot have 0 in the denominator of a fraction. So for the domain, that means that our denominator, which is sine of theta, that cannot equal 0. So let's solve that and find where will sine equal 0. So thinking about your unit circle, we're looking for y values, and the y values will equal 0 here at 0, as well as pi, and around again 2 pi, 3 pi, 4 pi, and so on. So those are all multiples of pi, so we know we can write that as pi times k. So these values are the values that you're not allowed to have in this function. So these are going to be the domain restrictions, in other words. So going back to our function, trying to find the critical numbers, we need to compute the derivative. Now, rather than using this newly rewritten function to find the derivative, I'm going to go ahead and use the original, and that's because I don't want to have to do the quotient rule. So I'm going to go ahead and just use my knowledge of derivatives. So the derivative of cotangent theta is going to be negative cosecant squared theta. And the derivative of 2 theta will just be 2. Now you can leave it in this form, or if you're like me and you want to go ahead and move towards a fraction, I would rather have everything written with sines and cosines. So I'm going to rewrite this as negative 1 over sine squared theta plus 2. In fact, I think I'll even go one step further and think about this as 2 over 1 and get a common denominator. So I can write this as one big fraction, which would be negative 1 plus 2 sine squared theta, all divided by sine squared theta, when I get a common denominator. And now we're going to branch off, and we're going to find our critical numbers by finding where the derivative is equal to 0, and where does this derivative not exist, or where is this derivative undefined. So, since this is one big fraction, we know the only way to make the fraction equal 0 is if the numerator is equal to 0. So I'll go ahead and set my numerator equal to 0 and solve that equation. And then the only way to make this fraction undefined is if the denominator is equal to 0. So I'll set sine squared of theta equal to 0 and solve that equation as well. So we'll add 1 to both sides as well as divide by 2, which will give us sine squared of theta is equal to 1/2. Then we will square root both sides. Don't forget when we're square rooting, then we'll end up with a plus or minus square root of 1/2 on the right-hand side. And if you want to go ahead and simplify that, you can. Not a bad idea here, because this is really the same as the square root of 1 over the square root of 2, which would be 1 divided by the square root of 2. And if you want to rationalize that and multiply by rad 2 over rad 2, then that's really going to give us sine of theta is equal to plus or minus rad 2 over 2. So we're looking for the angle that has a sine value of rad 2 over 2. So if you can remember some of your common angles, that's going to be a 45-degree angle, which will be pi fourths. But because it wants both positive and negative rad 2 over 2, that means that it could occur in any of the 4 quadrants. So the most efficient way of listing all of these angles, remember, notice, to go from pi fourths into the second quadrant, you'd be adding 90 degrees, you'd be adding pi halves. So a more efficient way of writing this would be pi fourths plus pi halves times k. In other words, we're going to keep adding multiples of pi halves. Now let's double check. Are these values in the domain? Let's go back and look. Over here for the domain, we said the domain would be all the values except for multiples of pi. So therefore, these are all going to be considered critical numbers. But resist the temptation to think that you're done, because don't forget there was the second branch, which was solving sine squared is equal to 0. So if you think of this as square rooting both sides, now sine theta is equal to 0. And again, on the unit circle, that's going to occur at 0 and at pi and around. So that would be theta is equal to pi times k, multiples of pi. But notice if you go back to that domain again here, we were not allowed to have multiples of pi. Those values were not in the domain. Therefore, these values are not going to be considered critical numbers since they're not in the domain. So the final answer for the critical numbers will just be theta values, which are pi fourths plus pi halves k.